Hello, this is lesson 9 in the use of JASP, and today we're focusing on the t-test with a special look at evaluating the normality assumption for t-test. So let's start by going and opening up from our data library a data set in the t-test module. This one's called kitchen rolls. We're going to first get rid of what's already there. And that just leaves us with the data set. There's about 102 people in this data set. And to focus our discussion, this is a study that was done as an attempted replication of another study that found that when people rotated an object clockwise, in this case kitchen rolls, they sit there and rotated it clockwise somehow, that basically promoted a sense of novelty, which resulted in them scoring higher on openness to experience, and they were somehow, I didn't read the details of the study, filling out the openness to experience questionnaire while rolling the kitchen rolls clockwise. In the other condition, they rolled it counterclockwise, and that was supposed to not yield as high of a score. So clockwise, counterclockwise, and our dependent variable is the average score on openness, which was measured with 12 items from the NEO, as you can see here, Q1 up through Q12. Okay, let's go ahead and click on t-test and go to independent groups. And we're going to go down to rotation and put that in as the grouping variable. We're going to take the mean of the NEO and put that in as the dependent variable. What comes up right away is that we have a t-test value of minus 0.754 with 100 degrees of freedom, and the probability value is 0.453, which is not less than 0.05, and hence that indicates what? That it's not statistically significant. You can add on to that the location parameter and the confidence interval. So if you look at the difference between the means, let's look at the means. Here's the descriptives. For those rotating clockwise, they averaged 0.641 on the NEO. For those going counterclockwise, 0.713. Now, first of all, you'll notice that this is opposite of what the first study would have predicted. And the first study found that it was higher for clockwise than for counterclockwise, and that's not what's found here. It's the opposite. Now, we also see that the difference is small. It's only, if you subtract one from the other, you get minus 0.072. We can look at the confidence interval, and the confidence interval goes from minus 0.263 to a positive 0.118. When you have a significant result, these two should both either be positive or both negative because they should not include zero. But here, zero is pretty much smack in the middle there. That minus 0.072 is in the middle between the lower row limit and, sorry, not the lower row limit, the lower confidence bound and the upper 95% confidence bound. So it appears that zero is definitely a possibility, so we cannot reject the null hypothesis. Today we're looking at the normality assumption. I want to look at that in a couple of ways. First of all, let's look at our rain cloud plots. We basically see evidence that there's no big differences here. We don't see any sign of major outliers in terms of the box and whiskers plot, sticking out from those. The distributions look reasonably normal. If we go ahead and click on normality test here, we see that we get the Shapiro-Wilks test, which is one of several tests, and this test comes out with a probability value of 0.266. It says here that significant results suggest a deviation from normality. So if it was 0.05 or less, then you would be suggesting that these curves here are deviating substantially from normality. But at 0.266, you can't conclude that. So the true distribution at the population level could be normal. Hence, we don't have a problem with the normality assumption. You can also look at the QQ plots. This is an interesting way of looking at the normality assumption. And as I will show you in the rest of this lecture, these data points should line up along a straight line, more or less, if the normality assumption is met. They would deviate, crossing maybe like so, really badly, if you had a major deviation from normality. The reason why the assumption is important, before we start looking at the distributions in detail, the assumption is important because we want this probability value to be correct. That's the probability of making a type 1 error, and we definitely want that probability value to be correct if it's less than 0.05, because if it's less than 0.05, we're going to reject the null hypothesis and say, aha, there's a difference between the two conditions. And if that probability value is not correct, then that's a problem. That probability value should be precisely correct, or most precisely correct, if the normality assumption is met. If the normality assumption is violated, then you have to worry that it's off a little bit. Here's the thing, simulation studies show that even if you violate the normality assumption, for theoretical reasons that I won't go into in depth here, the p-value tends to be pretty correct anyway. So you're not going to get major errors even if you violate the assumption. This is talked about in terms of saying that a test between means tends to be robust to the violation of the normality assumption, is how people refer to that. Now, that being said, let's take a look at this assumption in detail. We're going to look at distributions. And to do that, you'll need to go over to the plus sign over here on the right, go down here to these extra modules, find distributions, click on that, and add distributions up over here. Once you've done that, click on distributions, click on normal distributions, wait a second, and it gives you basically a perfect normal distribution, nice and smooth, as you would expect for a set of z-scores with a mean of 0 and a variance of 1 and a standard deviation equal to 1. Now, what we want to do is we want to look at this with respect to our data. And our data is using the mean of the openness score from the NEO. So we're going to put that mean over here. We're going to go ahead and click and ask for the first 2 moments. And a histogram and an empirical cumulative distribution. And that's one view of some things going on, but I think it's going to be clear. And so I'm just going to skip to where it's going to be clear if we go down to assess fit. But you can't go down to assess fit without at least putting this mean over here. And under assess fit, we're going to click everything. Okay, here's what I want to focus on. Once I've clicked everything, I get the moments about the mean. I said over here, it said first 2 observed moments. That's referring to the mean, which is the first moment, is what statisticians refer to it as, and the variance, which is the second moment about the mean. Skewness is the third, kurtosis is the fourth. We get 5 different tests that have been developed. The ones that you see in SPSS, or the KS is what I call it, because I don't like trying to say Kolmogorov-Smirnov test, so I just call it the KS test. You notice that one's not significant at all. The Shapiro-Wilk also shows up in SPSS, and that's 0.209. You have some other ones, and one of these is significant. Lillian-Ford's is significant at 0.022, but again, I wouldn't say that you have a problem unless these are significant at 0.01 or less, and I would use the Shapiro-Wilk or the KS would be my choices. So go to graphic displays. What's going on here? Why do we have a little bit of misfit in some of these tests? Why isn't it perfectly normal? What do these graphics tell us? Well, let's take a look at that. So this first graphic basically superimposes a perfect normal distribution for with a mean of 0.679 and a variance of 0.231, which fits this distribution. And then we actually see where the data are with respect to this distribution. We see some places where the data is gapping low, where ideally these bars should be lining up right along the normal distribution. Then it would be perfectly normal. That's a perfectly normal distribution if the data lines up perfectly. And when the data lines up perfectly, these data points over here line up perfectly along that line. So these are a reflection of these bars going either perfectly along the normal distribution or missing it. And what happens is with this distribution here, which is called a QQ plot, a quantile plot, it's basically saying, okay, well, where is the 25th percentile? Somewhere in here. Where's the 50th percentile? Over in here. And it's basically saying, okay, well, if I am looking at the mean over here, and the mean should be where the 50th percentile lies. Am I observing, how much data am I observing at that particular point? And what you see here is the gaps. Like this is gapping down. I think that's this gap right here. You see some other little gaps. I think those might be over here. You see over here at the top, it's starting to peak out a little bit. I think that's right there. And then you get a gap down over here. That's this gap over here. Here it's sticking out. This is very sensitive to the tails. And so you have a tail that's a little bit overexposed here. And so this one's kind of on the top of the line instead of being right on the line. So this gives you an easy way to visualize whether or not this distribution's normal. This is a cumulative distribution, and the cumulative distribution should be a nice little S distribution. And the reason why that's the case is because you should start off with very little data in the tails, none to then a little and then a little, and then you should get more and more, faster and faster and faster. So then this is getting up to the middle of the distribution, and it continues going fast, but it starts slowing down as you get down over here to this curve, and you should get less and less as you go over in here. This is called a PP plot, and the PP plot is a probability plot, and it's basically talking about, are the data points lining up on this cumulative distribution as they should probabilistically? And it has to start off with no data being at the very end of the tails. So there's no data over here. So that tends to match. And when you get up to the top, you should have observed 100% of the data. And so there's 100% of the data over here. And so this one is mapped onto this one here. You can still see little bits of this over here. You notice that what's happening is that the data is sometimes dropping off. You have a drop off here, and then it's catching up to where it should be. And so by the time you get up to here, you've observed about 50% of the data. It's not showing a big gap up because it's a cumulative distribution. The gap was earlier on the low side. We should have been filling in the distribution here, here, and here, and we weren't. But now that you have this big bar up here, it catches us up. So we're catching up to where we should be. And then we see a little gap up over here. And then we're kind of over where we should be, and then we kind of smooth on out. Anyway, both of these distributions are kind of fitting into their envelopes. And if they're fitting into their envelopes, most likely it's not, you have not violated the normality distribution, the normality assumption. So there's an in-depth look at how to look at distributions in terms of the normality assumption. I hope that helps you understand what's going on. There'll be more to come.